Welcome to the session on the subject electromagnetic waves and transmission lines. In this session, we shall be discussing one of the significant aspects of electromagnetic theory, that is the inconsistency of Ampere's law and its associated topic, that is displacement current density. To understand the perspective of this topic, inconsistency of Ampere's law is a problem that we are going to discuss. Displacement current density is the solution for that problem. Now that you know, there are two components in this discussion, namely the problem that was faced by Ampere. Inconsistency means there is some problem with Ampere's law when trying to integrate with other laws which form the basis for Maxwell's equations. That problem faced by Ampere is mathematically discussed under header inconsistency of Ampere's law, and the solution that has been got for that is the displacement current density. But the solution is not proposed by Ampere, it was proposed by James Clerk Maxwell. The problem is in terms of law which was postulated by Ampere, and the solution is given mathematically by Maxwell. That means essentially this topic starts with the mathematical formulation of the Ampere's law, and we see that Ampere's law is found to be not consistent in certain scenarios. There is a contradiction with what a postulate says with what a mathematical identity says. So this is called as inconsistency, and that happens to be for the Ampere's law. Now Maxwell worked on this Ampere's law to try to integrate this Ampere's law with other laws, namely Faraday's law and Gauss' law. For integrating effectively, seamlessly, or without any inconsistency, he has to invent a new mathematical term which is known as displacement current density. Now let us enter the discussion. First start with the inconsistency of Ampere's law. First, what is Ampere's law? Del cross H bar equal to J bar. Of course, this is in differential form because we have del cross means it involves dou by dou x, dou by dou y, dou by dou z, ax, ay, az determinant. So essentially this is nothing but the differential form of Ampere's law. We can also write it in integral form, integral h dot dl equal to I, that is enclosed. But let us take this form for our analysis further. This is the actual Ampere's law. Now let us try to apply a mathematical identity, a vector mathematical identity, that is apply divergence for this del cross H. That means apply del dot for the left hand side of the Ampere's law. Now you have to do the same thing in the right hand side also. So that is, because del cross H is J, that will be equal to del dot J bar. As per mathematical vector identity, the divergence of curl of any vector should be equal to 0. I repeat once again, the divergence of curl of any vector should be equal to 0. I am applying the divergence operation on the left hand side as well as on the right hand side. So it should be equal to 0, which means del dot J bar should be equal to 0. What is J bar? Yeah, electric current density. I means current, J means current density. Current density is a vector, so he is a bar here. So what does it mean? The divergence of electric current density does not exist. That is what it says. Now, is it so? In unit 1, we have seen what is called as del dot J bar equal to minus dou rho V by dou T. This mathematical relationship is named as continuity equation. The name of this relationship is known as continuity equation, a very important relationship. What it says? It says the divergence of electric current density is equal to the rate of decrease in the electric charge density. In this equation, on both sides you have densities. Del dot J bar is minus dou by dou T of rho V, continuity equation. What is this? Charge density. What is this? Current density. You have two densities on either sides of the equation, but what it says, the divergence of del dot electric current density is equal to dou by dou t means rate of, minus means a decrease, the rate of decrease in the electric charge density. Now, continuity equation says that del dot j bar equal to dou rho v by dou t. Here mathematical identity says that del dot j bar equal to 0. See, here you have del dot j bar, here you have del dot j bar. Here it is like saying, if I say del dot j bar is x, here it is like x equal to 0. Here it is the same x is, it is not 0, the right hand side is 0, which is non-zero. How can it be possible? I am saying x equal to 0, I am saying x is not equal to 0. It's like saying that you are white in color, you are black in color. So something should be correct. To avoid this contradiction, either x should be equal to 0 or x should be not equal to 0. Mathematical identity says that x equal to 0. An important postulate, continuity equation, says that x is not equal to 0. So this is what is called as the inconsistency. Sometimes saying x equal to y, sometimes saying x is not equal to y. This is what is called as inconsistency. Consistency means if x equal to y, it should be x equal to y forever, for all values, for all situations. That is called consistency. But here it is pure inconsistency. And that inconsistency we are facing in terms of, what is this? Ampere's law. Hence, inconsistency of Ampere's law, we say. Now, for this, Maxwell, James Clerk Maxwell, who is the person behind Maxwell's equations, hence the name Maxwell's equations, which are 4 in number. He tried to establish a relationship among Faraday's law, Ampere's law and Gauss' law. When he tried to establish a relationship among all these laws, it is something like joining the puzzles, taking the pieces and joining the puzzles and making a picture, a meaningful picture. When trying to establish a relationship, he is facing a problem with Ampere's law due to this inconsistency. So to solve this inconsistency, he invented a new term and he gave a name for that new term, which is displacement current density. Then he solved this inconsistency. Now let us see what Maxwell has done. The foregoing discussion, mathematical discussion, will be nothing but the mathematical invention of Maxwell. Now what Maxwell did? Del dot j bar equal to 0, del dot j bar equal to minus dou by dou t. Now he has taken the same thing again. If the right hand side here becomes 0, then there is no inconsistency. Here del dot j bar is 0, equation 1. Here also if this right hand side becomes 0, then second equation is also 0. That's it. Mathematically it is 0. Postulation wise it is 0. The problem will be solved. So what should be done to see that the right hand side becomes 0? I am saying first equation is 0, right hand side. Now second equation, right hand side is non-zero. What should be added in the right hand side of the equation 2 so that it becomes equal to 0? Now let us say this entire thing as x. You have minus here. So del dot j bar equal to minus x. If you add plus x, then what will happen? You get 0. So you have to add some term to see that the inconsistency is solved. What is that term? We don't know, because we are starting our discussion now. Maxwell has done it way back, hundreds of years back, but for us it is a surprise. We don't know that term, but we are going to add some term. Let us say del cross h bar equal to j bar. Add that unknown term plus n bar. For the time being, just say that n bar is some unknown term. We don't know what it is. What is the name? What is it equal to? We don't know. So in place of del cross h equal to j, take del cross h equal to j plus n bar. Now redo the same thing. Apply divergence on the left hand side and the right hand side. So del cross h equal to del dot j bar plus del dot n bar. By mathematical vector identity, it should be equal to 0. Now you know del dot j bar equal to minus dou by dou t. I have substituted here, plus what should be del dot n bar equal to, so that it becomes equal to 0. Here you have minus x, here you have plus x, then it will be equal to 0. What is x here? Dou by dou t. So what should be del dot n bar equal to? It should be equal to plus dou by dou t, minus dou by dou t plus dou by dou t. It becomes equal to 0. So what is del dot n bar equal to? What should we take in place of del dot n bar? Dou by dou t. So now you know this. But our objective is not to know what is del dot n bar. Our objective is to know what is n bar. What is that unknown term? But here we have del dot n bar. Now, trying to make the mathematical asymmetry in terms of operations. Left hand side you have a divergence operation. Try to invoke divergence operation in the right hand side as well. So for that, there is rho v here in the right hand side. There is one important relationship for rho v in terms of divergence. Then you get left hand side, right hand side divergences. And what is that important relationship? Del dot d bar equal to rho v. This rho v can be written as del dot d bar. Then you get in the right hand side del dot, already in the left hand side you have del dot. It becomes easier for simplification. And what is this law, by the way? The divergence of electric flux density vector is equal to the electric charge density. Of course, charge density is scalar, flux density is vector. Here also again you have two densities. On the right hand side flux density, left hand side charge density. Electric flux density, electric charge density. But you know mathematically the divergence of any vector should be a scalar. That's why charge density is a scalar. Flux density is vector. Okay. So in place of rho v, take del dot d bar. So that becomes del dot n bar equal to, left hand side equal to dou by dou t of time derivative of rho v equal to del dot d bar. So now we have del dot, del dot. Then you rearrange the terms. Take this d by dou by dou t here. It becomes del dot n b equal to del dot dou d by dou t. Del dot, del dot. So what is n bar equal to? N bar equal to dou by dou t of d bar. That unknown term is dou by dou t of d bar. And what is the name for that? Its name is displacement current density. The name of this term n bar is displacement current density, and that is equal to dou by dou t of flux density, electric flux density. Since we know what is n bar now you can substitute in place of n bar. Here in the beginning of discussion n bar is unknown, we don't know. Now we know what is n bar. So just substitute del cross h equal to j plus n bar. That n bar is dou d by dou t. This first term is referred as jc. This second term is referred as jd. Both are current densities. Suppose if I say this is 5 liters, this should be 1 liter or 6 liters, something like that. If I am taking liters, I should add liters for that. If this is kgs, I should add kgs for that. If this is length in meters, this should be also meters. I cannot say that this is liters, this is meters. 5 liters plus 5 meters. I cannot say like that. Dimensionally they should be same. So if this is current density, you know J bar is current density, then this should also be current density. But there are different types of current densities. The first one is known as JC, the second one is known as JD. Why JD? Just now I told you. Displacement current density. J bar means current density, D stands for displacement current density. J means current density, C means conduction current density. So the curl of magnetic field vector is equal to the sum of conduction and displacement current densities. That is the meaning of this equation. This is also known as modified form of Ampere's circuital law. I am specifying, I am not just saying Ampere's law, I am saying Ampere's circuital law. Because there is one more law, one more Ampere's law. What is that called? Yes, Ampere's force law. Similar to Coulomb's force law, we have Ampere's force law. Coulomb's force law deals with electric forces existing between electric charges. Ampere's force law deals with magnetic forces existing between electric conductors. Of course, they belong to different domains, but they are force law. So that's why there is one more law which is called Ampere's force law. What we have taken now, what we have worked with is not force law, it is circuital law, Ampere's circuital law. So what is the statement of modified form of Ampere's circuital law? The modification has been done by Maxwell. What is the modification? Adding a new term on the right hand side. Who has done that? James Clerk Maxwell. Why he has done that? Maxwell tried to establish a relationship among Faraday's law, Ampere's law, Gauss' law. He faced a problem with Ampere's law. It is not fitting in sometimes it is fitting, sometimes it is not fitting in some scenarios. To make it consistent, fit always, he invented this new term. So this is the historical and mathematical perspective of this discussion, which is known as inconsistency of Ampere's law, and the resulting Ampere's law is known as modified form of Ampere's law. Prerequisites for understanding the modified form of Ampere's law. Let us see the consequential things, what happens out of this, adding the second term, that is JD. Why do you say JC, this first term as JC, conduction current density? You have three constitutive relationships in electromagnetics. One is D equal to epsilon E, of course they are vectors, B equal to mu H, again vectors, J equal to sigma E. These three equations are known as constituent equations in electromagnetics. Now for the time being, just focus on this third one. J equal to sigma E bar. The current density is involving what? Sigma. What is sigma? Conductivity of the medium. Conductivity. Hence this current density is known as conduction current density, which is referred as JC. Conduction current density. Next, what about JD? JD is dou by dou T of D bar. What is D equal to? Epsilon E bar. This is referred as displacement current density. Why? Here you have sigma, conduction. Here you have epsilon, permittivity. Electric conductivity, electric permittivity. See, in circuits, if a current is flowing through a resistor, we say resistance of the resistor, or we say resistance of the conductor. Is the resistance infinite? No, it is finite resistance. If the resistance is infinite, then we say conductivity is 0. But it is finite resistance, which means there is some finite conductivity. So, the current flow through a resistor, let us say this is a resistor, the current that is flowing through its resistor comes under conduction current. And the equation for current here is I equal to V by R. V equal to IR, so I equal to V by R. Why I am discussing about current? Because we are discussing about current density. Its preceding quantity is current. Without current, we cannot discuss current density, isn't it? So, because our discussion is J bar, its prerequisite is I, current density. Now, on the other hand, take this scenario. If the same current is flowing through this capacitor, what is there inside the capacitor? Dielectric material. Between the plates, what is the dielectric material? What is the property of dielectric material? Permittivity, electric permittivity, which we say as epsilon. How the charge flows here? When you apply voltage across the plates of the capacitor, an electric field is developed. Electric field is nothing but the amount of electric force acting on a unit electric charge. That means with the application of electric voltage, there is a resulting electric field, and electric field is nothing but amount of electric force forcing the charge carriers. But in dielectric material, the charge carriers are bounded by the intermolecular forces. When you are applying electric field, which is nothing but an electric force, there is a displacement in the electric charges within the dielectric material. Displacement. Hence, this current is known as displacement current. Hence, the resulting current density is known as displacement current density. That's why JD refers to dou by dou T of D. D consists of epsilon. D equal to epsilon E. Epsilon is a property of dielectric material. Dielectric material is present inside the capacitor. Hence, all these things are so connected. Now, what is the equation for current here? Here it is I equal to V by R. Here I equal to C dV by dt. Equation for current here I equal to C dV by dt. Here I equal to V by R. See, the formula is also different. Here this is a formula. Here this is a formula. Different formulas, different contexts, different types, different current densities. So this is the background for JC plus JD. Now, out of our curiosity, let us try to characterize the medium properties, because unless you are sure or certain about the nature of the medium, you cannot know how the signal is going to propagate in that medium. Thorough understanding of the nature of the medium will help us in identifying the whereabouts of the signal propagation. How much signal gets attenuated, how far the signal can travel. See, the losses are more, signal cannot travel longer distances, the range falls. If the losses are less, signal can travel longer distances, so the range is more. So, how far the signal is supposed to travel, that is called range of propagation. How much the signal is getting attenuated per unit distance. These are nothing but characterization of the signal with respect to the medium in which the signal is propagating. For understanding that in a deeper sense, let us revisit the same equation, decompose this right hand side, break down it in two terms. One is JC, another is JD. Take mod JC, magnitude of that. What is JC equal to? Sigma E bar. What is the magnitude of that? This is real part plus what is imaginary part? There is no imaginary part here. So it will be 0 imaginary part. So what is the magnitude of that? JC by JD. JC is sigma E bar. JD, dou by dou T of JD is dou by dou T of D bar. That is dou by dou T of D is nothing but epsilon E bar. And the time derivative, the partial time derivative in time domain, of course T is there means you are in time domain, can be equivalently written as multiplying this quantity with j omega in frequency domain. That means dou by dou T, partial derivative of some quantity with respect to time is equivalently written as multiplying the same quantity with j omega in frequency domain, because omega is there means it is referring to frequency in frequency domain. The time domain lo dou by dou T of x ante that is equivalent to frequency domain lo j omega of x. That is the meaning. Now JC is sigma E, JD is j omega epsilon E. So E bar cancels. So what you are left with? JC by JD, sigma by j omega epsilon. What is this? JC by JD. But if you take mod JC by JD, magnitude of that, this is imaginary part. What is the real part? Nothing is there, 0. This is real part. What is imaginary part? Nothing is there, 0. So what is the magnitude of the numerator? Root of x square plus y square. Y is 0. So root of x sigma square, that is sigma, by denominator root of 0 square plus omega square epsilon square, that is omega epsilon. This is mod JC by JD. That is what I have written here. Now, what happens if sigma by omega epsilon is far greater than 1? What happens if this right hand side, by taking this JC by JD, we got this. Now focus on this. What happens if this is far greater than 1? This is nothing but sigma is far greater than omega epsilon. The conductivity is highly dominating the permittivity. Conductivity is a property of conducting medium. Permittivity is a property of dielectric medium. Electric conductivity is far greater than electric permittivity. Then the medium acts like a good conducting medium. Now, if sigma is far less than this condition, omega epsilon, conductivity is far less than electric permittivity. Permittivity is dominating here. Right hand side is greater. Permittivity is a property of dielectric material. So this medium acts like a dielectric medium. So this is how we characterize. Characterize means telling the character or behavior of a medium, whether it is conducting medium or dielectric medium. Why we take conducting dielectric is, for an electromagnetic wave, the preferred medium, the best medium is dielectric medium. And the worst medium, unpreferable medium is conducting medium. For electromagnetic wave. For electric wave, that is opposite. For an electric signal, the preferred medium is conducting medium. For an electromagnetic signal, the preferred medium is dielectric medium, which is opposite of it. That's the reason when it is raining heavily, you might have observed, nowadays every house is having DTH, direct to home connection. If it is raining heavily at your location, what will happen? Interruption happens in terms of TV broadcast. Why? You are receiving signals from the satellite directly to your home from the satellite, DTH. And what are the signals coming from satellite? They are not electric signals. Electric signals require a conducting medium, a wire, conductor, electric conductor to propagate. Electromagnetic signals can propagate out of nothing. They can propagate even from vacuum also. Nothing means vacuum. Electromagnetic signals can propagate even from vacuum also, even if nothing is there. So from satellite to your antenna on your rooftop, what is the signal that is coming? Electromagnetic signal that is coming. When it is raining, what is happening? Conductivity increases. Presence of water vapor, humidity increases, the conductive nature of the medium increases. And the conductive medium is the worst medium for electromagnetic signal. When it is raining heavily, there is severe conductivity in the medium. The electromagnetic signal suffers severe attenuation, so the broadcast stops. That's the meaning. For electric signal, the same conductive medium is the best medium. Suppose, assume that you are sitting in front of me 10 meters away. I have an electric wire in front of me. If I keep here, you don't get electric shock. Why? Because in between you and me, there is air. But if I fill the room with water and keep this wire in the water, even if you are 100 meters away, you will get the shock. Because water is good conductor, it carries electric signal. So for electromagnetic signal, the preferred medium is dielectric medium. For electric signal, the preferred medium is conducting medium. What is our subject? Electromagnetic wave theory. So what is our preferred medium? It is nothing but dielectric medium. What is the condition for dielectric medium? As I have written here, sigma by omega epsilon is far less than 1, which means sigma is far less than omega epsilon. So now, what happens if the frequency of signal increases? Or let us take this scenario, sigma by omega epsilon is far greater than 1. Or you can take sigma by omega epsilon is far less than 1. Take any one thing, I am taking this one. So this is sigma is far less than omega epsilon. If frequency of the signal increases, what will happen? Omega is nothing but frequency of signal. If it increases, what will happen? If it increases, the right hand side becomes stronger and stronger. On the other hand, if frequency decreases, omega keeps on decreasing. The frequency of signal is decreasing. So what will happen? The right hand side decreases. The right hand side is far greater than, because it is decreasing strongly, the right hand side becomes less than left hand side. What is that condition? If the right hand side is less than right hand side, the condition is nothing but, so I start by taking omega by sigma by omega epsilon is far greater than 1, sigma by omega epsilon far less than 1. Two conditions here. Now, first try to decompose this, break down this. Sigma is far greater than omega epsilon. If frequency goes on increasing, what will happen? The right hand side will go on increasing. When the right hand side increases very heavily, then this will become sigma is far less than omega epsilon. What is the beginning? Conducting medium. What is the ending? Dielectric medium. That means a medium which was behaving at like a conducting medium at change in frequencies, it may behave like dielectric, and vice versa. A medium which was behaving like a dielectric medium with a change in frequencies, this inequality gets flipped. It may behave like some other medium. That means there is nothing like perfect conducting medium and dielectric medium. Absolutely, you cannot say that. This medium behaves like conducting medium only. You cannot say for sure. If the frequency changes, this inequality may change. Far greater than may become far less than. Then it may start behaving like other medium. So this is very important aspect to be considered out of this modified form of Ampere's law. With this, we come to an end of inconsistency of Ampere's law and displacement current density.